deterministic. In a quantum program, probability results from measurement and collapsing quantum superpositions. In this program, the measurement of Q1 and Q2 may yield probabilistic outcomes. And at first, this seems like it could be the cause of the bug. However, something is still unexplained. Even if Q1 and Q2 have probabilistic measurement outcomes, how can they possibly affect Q3? The reason is the phenomenon of quantum entanglement. When two qubits are entangled, an operation like measurement on one of them can affect the state of the other. Specifically in this program, immediately before the measurement, Q1 and Q3 happen to be in an entangled state. As a result, measuring Q1 will probabilistically collapse the state of not only Q1, but also Q3, which causes the error. Knowing this, we can identify and fix the error. In the example, we should have used a different unitary gate, in this case CZ, which would break the entanglement between Q1 and Q3. In the fixed program, Q1 and Q3 are separable, another word for unentangled, meaning that the measurement of Q1 will not affect the state of Q3. In general, these kinds of unintuitive bugs are frequent in quantum computers because quantum entanglement is essential to quantum speedup. Quantum algorithms like Shor's algorithm for factoring or Grover's algorithm for search require entanglement to obtain an advantage over classical computers. What this means is that entanglement is essential to understanding the meaning of a quantum program. And understanding entanglement enables programmers to better write, debug, and optimize their programs. In our example, we would have liked to catch the bug, perhaps via some traditional technique like data flow analysis or abstract interpretation. However, the problem is that existing language frameworks cannot perform the necessary reasoning about entanglement, and current automated techniques like uncomputation are not sufficiently general to catch the bug like the one in teleport, meaning that in practice, developers will have to manually verify their programs by hand. In this work, we present Twist, a programming language that allows developers to soundly reason about quantum entanglement. It does so using a new semantic property, which we call purity. At a high level, purity is the property that an expression is not entangled with any other part of the program. Using Twist's language features, the developer can catch the bug in the example, repair the program, and be confident that the fixed program will satisfy its specification. As a preview, Twist's purity type system will prevent the entanglement bug in the example by determining that the output of teleport may contain entanglement, which would violate the specification. To repair the program, the developer uses Twist's purity assertion operators, which assert that expressions lack entanglement. The developer then verifies these assertions using Twist's static and dynamic analyses, which guarantee that a program that passes the analysis will satisfy its purity specification. In the rest of this talk, we're going to take a deeper dive into how entanglement affects quantum programming, how purity and the Twist language allow developers to soundly reason about entanglement, and how we evaluated Twist's design in practice. To understand quantum entanglement in detail, let's review the primitives of quantum computation. As you heard in the keynote yesterday, the basic unit of quantum computation is the qubit. For example, in this teleport function, we used 3 qubits named Q1, Q2, and Q3. A qubit is a superposition of classical bits, which here are denoted ket0 and ket1. It assigns to each of these classical bits a complex number called an amplitude. Just as we can concatenate multiple bits into a bit string, we can combine multiple qubits into a pure quantum state, which is a superposition of bit strings. For example, the teleport function initializes the quantum state of Q2 and Q3 to be a bell pair, which is a superposition of the bit strings 0, 0, and 1, 1. we can combine two quantum states by taking their tensor product. Here, the state of the overall program will be the tensor product of the state of Q1 and the state of Q2 and Q3. Quantum computation works by applying operations called unitary gates on these qubits. For the purposes of this talk, you don't need to understand the specifics of unitary gates. You only need to know that each one has a semantics that maps one quantum state to another. The last part of the program is measurement. When we measure a quantum state, we collapse it from superposition, getting a probabilistic outcome. Specifically, the result of a measurement is a probability distribution over pure quantum states. In quantum computing, we call these probability distributions mixed quantum states. Quantum entanglement means that the measurement outcome of one qubit can partially determine the state of another. To see what that means, let's consider what happens when we take the superposition of 0, 1 and 1, 1 and measure the first qubit in this system. Now, with equal probability, the quantum state will collapse to the outcome 0, 1 or 1, 1. The key thing to note here is that the state of the second qubit is always 1. And so the measurement of the first qubit has not really influenced the state of the second. We call a state like this one separable, which means unentangled. By comparison, consider this superposition of 0, 0 and 1, 1, which is called the Bell pair. When we measure the first qubit in this system, the result is either 0, 0 or 1, 1. Here, know that the final state of the second qubit is either 0 or 1, depending on the measurement outcome we got for the first qubit. So measurement of the first qubit has impacted the state of the second. We call such a state entangled. Another way to think about an entangled state is that an entangled state is one that we cannot write as the tensor product of two smaller pure states. In the example here, we could take our separable state and factor it as a tensor product of two individual qubits. There's no way to do this for the entangled state or any entangled state in general. Now that we have an understanding of entanglement, let's see how Twist reasons about entanglement using the semantic property of purity. So let's revisit the bug from the example and think about how a programming language like Twist might be able to catch it automatically. Remember that while the input to teleport was a pure state, we observed that its output was in a mixed state. How do we catch a bug like this one? So the key idea to our solution is that we need to enforce that Q3 is in a pure state rather than a mixed state at the end of the function. In particular, we do so by ensuring that Q3 is not entangled with Q1 or Q2 at the time that they are measured. So we'll need a semantic property that tells us that an expression in a program always evaluates to a pure state. We call this property purity. In the paper, we formally define purity operationally and denotationally. Here's the operational definition. We call an expression pure under a given quantum state if that expression evaluates to a unique value and final quantum state, and furthermore, the qubits that that value references are not entangled with any other qubit in the final quantum state. So what this means is that in the example, the second condition tells us that if Q3 is pure, then it cannot be entangled with Q1 and Q2 when they get measured, and measuring them cannot affect the state of Q3. Purity is integral to the design of the Twist language. Twist enables the developer to reason about purity using a type system, assertion operators, and verification analyses. Let's go over each one in detail. First, let's rewrite the buggy teleportation example in our language Twist. As you can see, in Twist, every quantum data type has an annotation, P meaning pure or M meaning mixed. A pure expression is one that is not entangled with any other in the program, whereas a mixed expression may be entangled. You can see here that as written, the return type of the function is mixed, and not pure like the input is. And this gives us reason to suspect that the function is implemented incorrectly. Let's see why the type of the return value has to be mixed here. In Twist, we represent entanglement using a type of entangled pairs, denoted using the ampersand type constructor. As you can see, the bell pair function returns an entangled pair of qubits. Now, this pair is marked pure in the program because these two qubits are entangled only with each other and not with the rest of the program. When we project two components from an entangled pair, Twist requires us to mark them as mixed because they're entangled with each other. For example, in this program, we mark Q2 and Q3 as mixed. Now in the buggy program, they continue to be entangled, and by the end, Q3 will be returned with mixed type. Next, let's see how to fix this program. On this slide, we've fixed the bug by using the proper unitary gate, CZ. We also want to ensure now that the return type of the function is going to be pure as expected. And we'll do that by adding a few lines of Twist purity assertions. First, we're going to create an entangled triple from Q1, Q2, and Q3, and it will have mixed type. Next, we use Twist's cast operator. This operator asserts that its argument is pure and casts its type to be pure. Then we use Twist's split operator. This operator takes a pure entangled pair and asserts that both of its components are pure. The result is that the return type of the function is going to be pure as expected, matching the specification. Now, how do we verify that the cast and split assertions are actually valid in this program? Twist's solution is analyses that automatically verify the purity assertions. First, it's going to verify cast using a sound conservative static analysis. To see how the static analysis works, let's try to check that at the time of the cast, this Q123 expression will not be entangled with any other expression in the program. To do this, we'll see that Q123 is composed of 3 qubits, and we're going to trace these qubits back through the program, looking for any other qubits that they might be entangled with outside of this set. Of course, we don't find any, and eventually we reach the input of the function and the output of bell pair, which we both know already are pure. Thus, the analysis can safely conclude that Q123 is pure. By contrast, Twist will verify the split assertion at runtime. Remember that split works on a pure entangled pair. So it suffices to test whether the two components of the pure are entangled with each other. Also recall that a quantum state is entangled if and only if it cannot be written as the tensor product of two pure states. The split operator simply tests whether the runtime quantum state can be factorized this way, and if not, it aborts the program with a runtime error. In the paper, we propose a primitive that tests whether the runtime state is entangled. We provide concrete implementations of this primitive on quantum simulators and discuss proposals for implementing it on hardware. Now that we've seen the design of Twist, including its purity types, assertions, and verification, let's discuss how it performs in practice. 3 key questions about Twist in practice are about its expressiveness and performance. First, is Twist expressive enough such that we can write well-known quantum algorithms in it? Next, can we give programs meaningful purity specifications such that Twist will be able to detect bugs in their implementations that would violate these specifications? And third, what's the overhead of executing these runtime assertions in Twist? First, let's evaluate Twist's expressiveness. We implemented Twist on a quantum simulator and wrote a suite of benchmarks, including well-known quantum algorithms such as Deutsch's algorithm and Grover's algorithm, as well as Shor's error correction code. In this table, we present the results of Twist's type checker, static analysis, and runtime checks on the benchmarks. The valid column denotes the ground truth of whether the program satisfies its purity specification. As you can see, for all but one program, Twist precisely concludes that the programs satisfy their purity specifications. Now, in one case, the static analysis was sound but overly conservative, and we invite you to see our paper for why this was the case. Next, let's examine whether Twist's analyses are soundly rejecting invalid programs. We modified several of the benchmarks from the previous table to introduce a subtle bug, such as changing or removing a critical quantum gate, such that they'll no longer satisfy their purity specification. As you can see, in all cases, Twist soundly determines that the programs are invalid, either statically or at runtime. Next, we wrote a family of programs to examine Twist's runtime performance. They use a purity assertion to verify that after a conditional modular multiplication followed by an inverse, the condition qubit should be separable from the data qubits. We executed these programs on a quantum simulator and measured their total runtime and the proportion of runtime spent checking the purity assertions. This graph plots the portion of runtime that was spent verifying the runtime assertions. As you can see, the overhead is low overall. It never exceeds 3.5%, and it diminishes as the number of qubits in the program increases. Please see our paper for more detailed experiments. Twist opens the door to several interesting questions. First, the static analyses could be made more precise under classical control flow. As we saw, it can currently be overly conservative. Next, in the paper, we briefly describe the implementation of separability testing in quantum hardware. But more study is really needed to understand the practical implications and viability of doing such a test in hardware. Also, we should extend Twist's entanglement reasoning to other quantum languages with features such as automatic uncomputation that make life easier for the developer. To conclude, in this work, we presented Twist, a new quantum programming language that allows developers to soundly reason about quantum entanglement. It does so using a new semantic property called purity, and using a type system, assertion operators, and verification analyses for purity. You can find Twist in our artifact and also on GitHub. Finally, if there's one thing you should take away from this talk, it is that programming quantum systems will require us to understand difficult quantum phenomena such as entanglement. If we can build the proper language abstractions, we can turn entanglement from a cognitive burden for developers into a practical tool. Thanks for listening.
All right, so to attempt to keep things a little bit close to time, I'll take one question from the room if there is one. Great. There is a question that's from a remote participant, Charles, so I hope you can answer that after the session ends.
Okay.
Can you just hi? Can you just speak a bit more about the separation, the dynamic analysis, how it's implemented, and you mentioned something about quantum hardware, but can you just flesh that out a bit?
Exactly, right. So in the paper, we basically propose a primitive that does the separability testing on the runtime quantum state. Now, this primitive will be implemented differently in quantum simulation versus hardware. In simulation, it's basically a linear algebra operation, and it's fairly efficient given the typical state vector representation in a simulator. In quantum hardware, it's a much more complicated task, right? Because separability testing is a form of quantum state tomography. It happens to be a form that is more tractable than usual tomography. And the usual work on separability testing in hardware is, I believe it's Harrow and Montanaro have a paper on this. They propose a swap test that can perform separability testing using 2 copies of the quantum state. It's a relatively low number of copies. And I believe you can generalize this to a test that operates in O of 1 over epsilon squared for some choice of epsilon closeness to a separable state.
Okay, thank you very much. And we'll now